Ever really stop to think about what goes into building a modern airplane? Well, today we're going to do just that. We're going inside these incredible flying machines to pull back the curtain on how they're built and, more importantly, the physics that actually keep them in the sky. You know the feeling, right? I think we've all had that moment. You're cruising along at 30,000 feet, you look out the window at the clouds below, and it just hits you. How is this giant metal tube weighing hundreds of thousands of pounds just hanging up here? It honestly feels like it should be impossible, but it's not magic, it's just some seriously brilliant engineering. And really, the secret sauce boils down to two main things. First, learning how to control a bunch of invisible forces, and second, inventing materials that are somehow both lighter and stronger than steel. So let's start with those forces you can't see. To get how a plane flies, you first have to get the physics. See, there are four fundamental forces that are constantly in a tug of war on any airplane. And the whole secret to staying airborne is just managing that constant conflict. Okay, first up, you've got the vertical battle. You have weight, which is just gravity, relentlessly pulling the plane down towards the earth. But fighting against it, you have lift. This is that magical upward force that the wings generate as air flows over them. And it's simple. To get off the ground and stay there, lift has to be stronger than weight. At the exact same time, you've got this horizontal battle going on. The engines are creating thrust, which pushes or pulls the plane forward. But the air itself fights back with drag, creating resistance on every single surface. So to move forward, thrust has to overcome drag. So here's the key takeaway. When you see a plane just cruising along, not climbing or descending or changing speed, it's because those four forces have reached a perfect stalemate. Lift is exactly equal to weight, and thrust is exactly equal to drag. It's this incredible, high-speed balancing act. Now, actually controlling the airplane means the pilot is deliberately unbalancing those forces along three different directions. You've got pitch, which is the nose pointing up or down. You've got roll, which is when the wings bank to the left or right. And then there's yaw, which is the nose moving side to side. Pretty much every single maneuver a pilot makes is just a combination of these three movements. Okay, so we've got a handle on the forces. Now let's look at the actual physical parts of the plane that make it all happen. You can break down just about any aircraft you see into five major components. You have the fuselage, that's the main body. Of course, you have the wings. Then there's the empennage, that's just the fancy word for the tail. You've got the landing gear. And finally, the power plant, which is basically the engine. Let's take a quick look at each one. The fuselage is the heart of the plane. You can think of it like the central hub that everything else plugs into. It's where we sit, where the cargo goes, and it provides the main structural backbone that holds the wings and tail assembly together. The wings, well, they have the most famous job, right? They create lift. That special curved shape they have, it's called an airfoil. It makes the air passing over the top move faster than the air underneath, and that difference in pressure creates an upward pull. But they do more than just that. They're also what allows the plane to turn by controlling its roll. So how do wings do that? They use these movable surfaces on the trailing edge. On the outer part of the wing, you have ailerons. When one goes up, the other goes down, and that causes the plane to bank and roll into a turn. Then, on the inner part of the wing, you have flaps. These extend downward to create a ton of extra lift at slow speeds, which is absolutely critical for takeoff and landing. All right, on to the empennage, or the tail. This whole section is all about stability and control. The big vertical part with its rudder, that controls the yaw, the side-to-side motion. And the two little horizontal wings, with their elevators, they control the pitch. That's the up and down pointing of the nose. And last but not least, the power plant, the engine and the propeller. Now, the engine makes the power, but it's the propeller that really does the work. And here's the cool part. A propeller is basically just a wing that's spinning around. So just like a wing creates upward lift, a propeller's rotation creates forward thrust, literally pulling the plane through the air. So we know the parts, but what are they actually made of? Well, that answer has changed a lot over the years. We've gone from simple wood and fabric to some really futuristic space-age materials. The earliest planes used what's called a truss structure, basically a cage of wood or steel tubes covered in fabric. Strong but not very smooth. The next big jump was to a monocoque design, where the outer skin itself carries all the structural load. Think of an aluminum soda can. It's strong because of its shape. Today, we use a hybrid called semi-monocoque. This is where you have that stressed outer skin, but it's reinforced by an internal skeleton of frames and stringers, making it incredibly strong and resilient. But the real game changer, the latest revolution in how we build planes, is the shift to composite materials. We're talking about things like carbon fiber and fiberglass. This stuff has completely rewritten the rulebook for aircraft design. And the advantages are just massive. You can mold composites into these incredibly smooth, complex shapes that cut down on drag. They don't rust or corrode like metal, and the big one, they can be engineered to be unbelievably strong while weighing way, way less than the equivalent aluminum part. But, and this is a big but, there are downsides. The biggest headache with composites is that a simple, low-energy impact, like someone dropping a tool on a wing, can cause serious damage inside the material, with absolutely no visible mark on the surface. This hidden damage is a huge safety concern. They're also pretty sensitive to high heat, and you can't use normal chemical paint strippers on them. Okay, let's step away from the airframe and look at the brain of the aircraft, the cockpit, because the transformation that's happened in here is just as dramatic as the shift from wood to carbon fiber. I mean, this picture says it all. On the left, you've got your classic analog cockpit, just a sea of individual mechanical dials. And on the right, a modern glass cockpit. All of that scattered information is now consolidated onto two main computer screens, the primary flight display for your must-know info and the multifunction display for everything else. And the benefit here is just enormous. It totally declutters the pilot's field of view, it reduces their workload, and it makes critical information pop right out of you. Not to mention, these digital, solid-state instruments are just worlds more reliable than the old mechanical ones, which is a massive leap forward for safety. And that kind of brings us to our final thought here. From simple truss frames to complex composites, from a wall of analog dials to sleek glass cockpits, the modern airplane has become this incredibly sophisticated, data-driven machine. It really leaves us with a fascinating question. As this technology keeps getting more and more automated, how does the fundamental role of the human pilot change right along with it? What does it even mean to be a pilot in the age of automation? Something to think about next time you find yourself looking out that window.